Okay, so we are going to take a look at some buffer calculations. In order to do that, we're going to derive the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation allows us to skip all of these ice tables that we've been doing, and it makes our life significantly easier whenever we're talking about a buffer. And then we're going to identify what a buffer is and how to know that we're actually using one. But again, we should know this already. Like acid and its conjugate base. If those two things together in a solution, we have a buffer and we can use this equation. And I'm telling you, this is significantly easier. In fact, I'm going to show you how much easier it is. So let's consider the equilibrium expression for a general weak acid. So H plus and A minus, products over reactants. There we go. I'm going to rearrange this equation just a little bit. Ka is equal to the concentration of H plus times the concentration of A minus. I'm just going to keep those two terms together, HA. And now I'm going to take the negative log of both sides. I'm just going to take the log of, I'm going to take the negative log of both sides. So we're going to get the negative log of Ka is equal to negative log of the concentration of H plus, okay, plus the log of concentration of A minus all over concentration of HA. Again, I'm treating that like one term. I've separated these two out by the plus sign. So essentially, because I'm multiplying this, log of this plus log of that gives me the whole thing. Okay. Okay, so now we are going to recognize that actually what we have here is this negative log of the Ka becomes the term pKa. This term right here becomes pH, and we're going to leave the other term alone. So I'm just going to rearrange this equation. But ultimately what we have is the pH is equal to the pKa plus log concentration of the base over the concentration of its conjugate acid. This is it. This is what we are interested in. This is the one we need to know. This is the one we need to memorize. This is the one you're generally given, but this is the one you need to know. This is called the Henderson-Hasselbalch equation. The pH of a buffer is equal to the pKa of the buffering system, so the acid that is part of the conjugate, and its concentrations of its conjugates, base over acid. And there you go. We're going to be able to solve for pH incredibly quickly. This is an incredible shortcut. You need to know this equation. It's so important that you know this equation. So let's take a look at something like this here. So calculate the pH. What is the pH of a buffer? So what is the pH of a solution that is? Again, if we had, let's do this, we're going to do this in two ways. The first way that we're going to do it is we're going to look at it from an equilibrium or an ice table point of view. Okay, so let's say how we would normally do this. So what is the pH of, okay, so some solution. The pH is, again, H plus, concentration of H plus at equilibrium is ultimately what we need to find in order to calculate the pH. We know that it is 0.12 molar lactic acid. And there's my lactic acid nightmare right there. Okay. And concentration is 0.1 molar sodium lactate. And I don't really care about the sodium part. All I want is the lactate. Okay. So what I know is we have HA. Again, this whole thing here is going to be my A minus. And then the H part is going to be the H plus. Okay. Just like the sodium can be ignored, this whole thing here is going to be the A minus. So HA dissociates into H plus and A minus. Okay, there we go. We have our initial change equilibrium. And of course, so let's figure out what we already have. So before we even continue, Ka is equal to concentration of H plus times A minus all over concentration of HA. And we know the Ka is 1.4 times 10 to the negative 4. So what do we know? What do we know already? We know that the concentration of the acid is 0.12, and we've already done a couple of these calculations. We know the concentration, we don't know the concentration of H plus, there's no mention of it. We know we have some A minus here at 0.10. So we know that we're losing this because we need to gain some H, and we're gaining that because it's a 1-to-1 ratio. So again, we're going to make the assumption that it's small 0.12 X and 0.10. We're going to make those assumptions. So we have equilibrium values. Fantastic. So now what this means is we can actually substitute these values in. My H plus is my X. My concentration of A minus is 0.10. And concentration of HA is 0.12. Solve for X. We solve for X, which is also concentration of H plus. Concentration X is equal to 1.68 times 10 to the minus 4. And then the pH is equal to the negative log of that value. The pH of the solution is 3.77. There we go. Done. We got the pH. Easy enough. We know how to do these. We're becoming pros at this. So the next question is, how can I make this easier for myself? Well, we're going to use the same thing, but this time we're going to use the Henderson-Hasselbalch equation. So again, I'm going to pull the information. Again, I'm going to have pH is equal to the pKa plus log of the concentration of the base over concentration of the acid. And we actually already know these values. So we're solving for the pH. What we know about pKa is just simply negative log of the Ka. And we already have the values of the plus log of the base over acid. So we know that my base is 0.10 molar and 0.12 molar for the acid. So let's plug in values here. So the negative log of 1.4 times 10 to the minus 4 plus log of 0.1 molar over 0.12 molar. Okay. What you end up with is 1.85 plus a negative 0.079. And your pH is equal to, if you do that calculation, 3.77. Notice it's the exact same as we just got, but that one was significantly quicker to just plug all those values in. That's it. A couple of things that you can think about is if you have more base, more acid than base in terms of concentration, we expect a pH to be less than the pKa, and vice versa. Okay, so just to double check yourself, your base should, if your acid is greater, your pH should be lower than the pKa, and if your base is greater, then your pH should be greater. Okay, and if they're equal, well, we have to have a conversation about that, and that's to talk about the pH range. So the pH range of a buffer. So this is the pH chart. The difference here is, instead of this being, so the very first one we looked at, the very beginning of the last, was a weak acid, or a strong acid, strong base. This is a weak acid with a strong base. So we have volume of alkali or volume of NaOH is typically what you look at. So this is what the curve looks at. So usually what you see for a strong acid and base, you see the equivalence point and it always occurs at 7. Okay, but it's very quick. It's flat, 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 straight up base, and that's what we got. What this has is it goes up pretty slowly, and then you get a climb, and there's a reason that this is basic, and we're going to talk about that now. So let's consider the positions that we have. At the very beginning, okay, I have 100% HA and 0% A minus. Okay, so the pH at that point is just a simple ice table. You can't use Henderson Hasselbalch here, and there's a reason for this. At the equivalence point, this is when the moles of acid have been completely gobbled up by the moles of base. And at this point, I have 0% HA of my acid, and I have 100% A minus in solution. And we're going to see how we can actually do the calculation for A minus. We look at bases instead. So we look at how much base we have present, and we could do those calculations just in reverse. In fact, we've already looked at that. You should have seen that in the end of the first one. But again, this is just a nice table. You should know how to do all this. This is not buffer stuff at all. Okay, so we're a couple of things. We're going to call this right down here. This is known as the E, or the volume of the equivalence. Okay, so that's the volume. It took me 25 mils to completely neutralize this. At the beginning, I should have 0 milliliters. Okay, so what I want you to think about is what is going on at the halfway point. So if we look at this halfway point, this is going to be special. So this halfway point, which we mark down as a special 1/2 VE, which you can actually calculate. We know this is 12.5 mils in this case, right? So this 1/2 volume of equivalence, I know I have 50% HA and 50% A minus. I have 50% of each. So if I think about the Henderson-Hasselbalch equation at this point, so pH, because pH is equal to pKa plus log of the concentration of the base over the concentration of the acid. So as soon as I add first of all, before I even add anything, we cannot use Henderson-Hasselbalch, but as soon as I add 1 drop of acid, so this whole region here, this is known as the buffering region. Okay, so this whole region is the buffering region as soon as I start to add the conjugate, as soon as any of the conjugate is present. In fact, I didn't even add any A minus, I just added OH minus, which converts HA to A minus, and we're going to talk about that in a bit. That whole region is called the buffering region. Okay, so yeah, buffering region. Now, if we consider what's going on at that 50% mark right here, right? So we want to kind of take a look at that spot right there, okay? So what we know at this moment is we have 50% HA and we have 50% A minus, okay? So in that moment, what is 50% over 50%? This whole value is essentially just going to go to 1. So if that value goes to 1, what is the log of 1? The log of 1 happens to be 0. So this whole thing is plus 0, which means this whole term essentially just goes away or deletes itself, goes to 0, which means at this moment, the pH equals the pKa. So the pH equals the pKa at the 1/2 volume of equivalence. So what that means is we can actually determine the pH at this point, okay? And it's going to give us the pKa. So we have another opportunity to actually determine the unknown of an acid. So I could determine the unknown of an acid by looking at the 1/2 equivalence point, because the pKa should equal the pH, because that's how buffers work. So it's a really useful little way to help us identify an acid among other ways. And we're going to try to get some of that done as well. So we're going to talk about this idea of buffer capacity. Basically, how strong is my buffer? So a couple of things. So what makes a good buffer? First of all, what is required? A conjugate acid and base. And there's a couple of ways we can make this, and we're going to talk about that in a moment. But you need conjugate acid and base. You really need a high concentration. This is actually, after you have acid and base, the higher the concentration, the better off you are. And the pKa close to pH of the buffer, that's going to make a good buffer, because ultimately what that leads to is a ratio of A- to HA close to 1. And that is going to give us the most push on either side. It's going to act as a good acid or base buffer. So those are the things. Higher the concentration is generally the best way to do it. You need that conjugate acid base pair, but pKa we generally want as close to our buffer as possible. So understanding what occurs when we add an acid to a buffer is kind of the most important, like the easiest way to do this calculation. So if we take a look at this problem, so calculate the pH of the buffer change. So a buffer is made by adding 0.3 moles of 0.3 moles of, ultimately what we can actually do is if we ignore volume in our Henderson Hasselbalch equation, we just have to find moles. So if you can find moles, you can actually just skip actually doing any volume calculations whatsoever. So a buffer is made by adding 0.3 moles of HCO, basically acetic acid, and 0.3 moles of sodium acetate to enough water to make 1 liter. Okay, the pH of the buffer is 4.74. We know that because we have, all right, it's the pH of the acid, or this is my HA. This is going to be my A-. Again, I don't really care about the sodium part. To make 1 liter of solution, and the pH, notice that we're at a 1-to-1 ratio. So the pH of the buffer 4.74, which is actually the pKa as well. Calculate the pH of the solution after 0.02 moles of NaOH is added. Okay, so first of all, we know that pH is equal to pKa plus log of the base over the acid. Again, if both of those concentrations are in the same volume, and they are, then we can actually just ignore the volume component of it, and we just plug moles in. So that's what I'm going to focus on now. Okay, so we need to plug in moles of base over moles of acid, because I know the pKa is 4.74. And the reason that I know that is because this right here, because it's a 1-to-1 ratio, this is the pKa, because HA equals A-, right? So if that's the pH, then that's the pKa. Okay, yeah, let's take a look. So what do we start with? What we start with is some gray, sure, 0.3 moles, 300 moles of HA, and 0.300 moles of A-. Okay, and then we add NaOH. What we're really adding is just OH-. What happens to these two things when I add OH-? Okay, well, what is the NaOH, or what is the OH- going to actually interact with? So if I have OH- being added, we know that it's going to interact with which one of these two? Well, it's not going to interact with anything that's negative. It's going to interact with the acid present. So OH- is going to interact with the HA, which is my acid. So when those two things react, I end up with H2O, liquid, plus A-. Okay, so what has happened here is I have taken my HA and I've converted it to A-. So for every single OH- that reacts, I take one HA and convert it into one A minus. So what that means is for every HA, I'm converting, so I'm adding 0.020 moles of OH minus, right? And I am converting those moles of OH minus or HA into A minus. So that is the conversion that we're doing. Okay, so what you end with is 0.280 moles of HA and 0.320 moles of A minus. And now all it is just a matter of plugging these values in. Plus log, the base is 0.320 over 0.280. Again, I don't care about the volume because we can just simply, because the volumes are the same, so they're just going to cancel out. So 4.74 plus 0.058, and that makes sense because I actually have, oh, I did that upside down, didn't I? Actually, yeah, the pH is going up. Yep, that's correct. A minus is larger, and so you end up with 4.80, and that is my pH. That's it. That's the solution. That's how you do it. So same way we do a titration, but we're just going to make the changes in the buffer. Okay, good. So let's talk about how you make a buffer. People struggle with this for some reason. There are 3 ways of making a buffer. First of all, our goal to make a buffer. Making a buffer, all that simply means is what I need to do is I need to get HA and A minus in the same solution. So whatever I can do to get HA and A minus in the same solution, we're a winner. That's it. So if I have a weak acid, okay, so weak acid, HA, and I combine to it. So I don't know, have a liter of water and add some acid to it. Congratulations, we've got weak acid. So, and I'm going to add to it a weak base. And these typically come in the form of salt. So weak base salt, like sodium acetate. That's the, so this weak acid be acetic acid and sodium acetate. And the weak acid is always going to become as like a group 1 with the base. So sodium acetate, sodium lactate, something like that. Mix those 2 together in the proper ratios, boom, using Henderson Hasselbalch, I've got my buffer. That's it. The other option is we start with a weak acid, HA, and we react that with some strong base. The strong base comes in the form of OH minus, but again, the whole goal is just to simply get those 2 things in the same solution. So there's my HA, there's my A minus for weak acid, weak base. There's my HA. If I combine HA and OH minus, again, what we're going to notice is I'm going to create water and A minus. So again, for every single OH minus I add, I'm converting one of the HAs present into an A minus. So we've done it. We can create the A minus in situ or in solution. Okay. All right. Hopefully you see where I'm going with this. The other option we have is a strong acid, which is just simply H plus, and a weak base salt, which is going to be A minus. Again, I already have the A minus, but if I combine the A minus with the added H plus strong acid, you end up with HA. So again, same idea. We got both of those in solution and we have done it. So that is it. That is our solution. Good. All right. So what concentration of NH4Cl salt is needed to bring 0.1 molar NH3 solution to a pH of 9 in the KB. So we have all base terms here. So first of all, we can do this in a couple of ways. We can do this so to a solution of pH of 9. So we can actually backwards calculate this if we wanted to figure out what we needed X to be in order to solve for these values. But let's just isolate what we need. And we're actually going to work out this in class. But if we want to switch the Henderson Hasselbalch pKa plus log of the concentration of base over the concentration of acid. If we want to, this is the acidic version of it. If we want to do the basic version of it, we actually just flip everything. So POH, right? So we're matching these things up. POH becomes equals PK instead of pKa, pKb. pKb plus log of, and now I'm going to actually flip these two. I'm going to flip these, and it's going to be log of concentration of acid. Right now, HA all over concentration of A minus. There we go. And this is the basic version of it. So we could actually solve this by simply, and we could actually solve this both ways. Okay, so we could simply say, first of all, let's just isolate what we've got. What concentration of NH4Cl salt is needed to bring this solution? So I know that this right here is this is the base portion of it. So this is actually A minus. The NH4Cl salt, although I've been telling you that this is the acid or the base, this is actually going to be my acid, HA. So I'm asking, what does the concentration of that have to be? To a pH of 9, right? So I need a pH of 9 in the end, and I have the pKb value. So let's use the Henderson-Hasselbalch equation that we know. So pH is equal to 9. pKa, well, I have the pKb, or I have the Kb, and what do we know about Ka to Kb? So I'm just going to take this. So there's a room up here, sure. So what I do know is Ka times Kb is equal to Kw. So I can actually do this conversion. I can just simply say my Ka value times the Kb value of 1.8 times 10 to the minus 5 is equal to 1 times 10 to the negative 14. And I can do that calculation. What you end up with is, let's see here, 5.6 times 10 to the negative 10. So my pKa is negative log of the Ka, which is 5.6 times 10 to the negative 10, okay? Plus log of the, and so here's the interesting part. I'm actually going to be solving for this ratio. So I just have to figure out what this is and then take the base 10 of it. So log of my acid, my base, which is 0.10 all over my acid. I'm looking for this HA. What concentration value do I need here? Okay. And so we can actually just solve, we can actually just simply go through this and do this calculation. So 5.6 to EE or EXP to the 10th plus or minus, take the log of that, take the negative log of that, and you have 9 is equal to 9.25 plus log of 0.10 all over concentration of HA. Okay, so let's take 9, let's do the next part. So 9 minus 9.25 gives me negative 0.25 is equal to the log of my value here, 0.1 all over concentration of HA. Okay, so then raise both sides to the 10th. So 10 base 10, we end up with 0.56 is equal to 0.1 over concentration of HA. My God. Okay, and then so 0.1 divided by the 0.56 gives me concentration of HA is equal to, I just switched those spots and then did the division, 0.18 molar. So I have to add a solution of 0.18 molar in order to get that done. And that's it. Okay, so that's how we solve that problem. Let's try it from the other point of view. So POH. So if I have pH plus POH is equal to 14, right? So POH is equal to 14 minus the 9, which is equal to 5. So POH is equal to 5 equals the pKa or pKb of negative log of the Kb, which is 1.8 times 10 to the minus 5, plus log of the acid, which we don't know, HA, all over A minus, or I'm sorry, over 0.10. And now let's do some work. So 1.8 exp negative 5. I take the log of that, the negative log of that. We have 5 is equal to 4.74, I guess I don't know if that was right, but it doesn't matter. 4.74 plus log of HA all over 0.1. Again, because I flipped that, right? Now the base acid on the top, the base is on the bottom. So 5 minus the 4.74 gives me 0.26 is equal to the log of those two, HA all over 0.1. Take the 10 of both sides, the 10 base of both sides. So 10 base gives me times 0.1. Yeah, that's it. So 1.8, we end up with 1.8 on this side is equal to concentration of HA all over 0.1. And then you do the math, you multiply that out, HA is equal to 0.18 molar. So either way works. So you can do it from the base point of view or the acid point of view. That was the kind of point of that whole lesson. Good. All right. And then we can do those calculations to figure out how much salt you're supposed to add. How would you create this buffer? I've got a volume here. Don't worry about the volume. Just see if you can come up with the proper ratios, proper amount. Same thing here. And we've got some other ways to make buffers. But that is it. That's the buffer work. And we'll take a look at it more later.